All right, so we've got some really interesting stuff to dive into today, all about continuity and differentiability of functions. And we're pulling this straight from some pretty classic mathematical texts.
Yeah, some really cool concepts here.
Yeah, and our mission, if you will, is to take these ideas, which can seem pretty abstract, all about limits and derivatives, and try to make them not just clear, but actually insightful, so you can see how they play out in the real world.
Absolutely. And I think you'll be surprised how these concepts pop up in so many different areas, even if you don't think of yourself as a hardcore math person.
Right, exactly. I mean, we'll be looking at all sorts of functions, simple ones like polynomials, but also getting into the nitty-gritty of things like trig functions, sine and cosine, and then even exponential and logarithmic functions, stuff that can really make your head spin if you're not careful.
Yeah, for sure. But we're going to take it step by step, and we're going to try to do it in a way that's not just a lecture. We want this to feel like a conversation, like we're all just figuring this out together.
Exactly. So let's start with continuity, which the book, I love this, describes as being able to draw the graph of a function without ever lifting your pen from the paper.
Yeah, it's a great visual analogy.
It is, and they actually give some examples where that pen lift is needed. Like, imagine a function where at x equals 0, the graph suddenly jumps up, right?
You're right. Like it goes from, say, a height of 1 to a height of 2 instantly. There's no smooth transition.
Exactly. So you have to lift your pen to get to that higher point, and that jump, that's a discontinuity.
And there's another type of discontinuity they show where you have this smooth line, let's say at a height of 1, but then at a single point, like right at x equals 0, it spikes up to, let's say, 2, and then instantly drops back down to 1.
Okay, interesting. So even though it sort of approaches 1 from both sides, that single point where it jumps up creates a break.
Exactly. It disrupts that smooth flow, even though it's just at one single point.
Okay, so that's a good intuitive sense of what continuity feels like, this smooth, unbroken line. But to be really precise, we need a more formal mathematical definition, don't we?
Absolutely. And the book defines it like this. A function, let's call it f, is continuous at a point c if the limit of fx as x approaches c is equal to fc.
Okay, that's a mouthful.
Okay. Yeah.
But if we unpack it, it's basically saying that as x gets closer and closer to c, the value of the function has to approach the actual value of the function at c.
Right, and that's where things can get tricky because there are actually a few requirements baked into that definition.
Like what?
Well, first off, the function actually has to have a defined value at c. Like in that second example we talked about, if the function isn't defined at that point where it spikes up, we can't even talk about continuity there.
Right, makes sense.
Then you need the function to approach the same value whether you're coming at c from left or the right. If it's approaching 2 from the left but 1 from the right, that's a no-go for continuity.
Ah, so those one-sided limits have to match.
Precisely. And finally, that value it's approaching has to be the same as the actual value of the function at c. If those two things are different, then you've got a discontinuity right there.
Okay, so it's like a three-part check. Defined value, matching limits, and those limits equaling the function value.
Exactly. If any one of those fails, boom, discontinuity.
Now, the book goes through some specific examples to illustrate this. Maybe we can walk through a few of them together. Let's start with a simple one. Fx equals 2x plus 3 at the point x equals 1.
Okay, perfect. So first, we plug in 1 for x, and we get 2 times 1 plus 3, which is 5. That's our f, say, our function value at x equals 1.
Okay, so far so good.
Now think about what happens to 2x plus 3 as x gets really close to 1, but not quite equal to 1. It's going to get really close to 5, right? Like if x is 0.9, then 2x plus 3 is 4.8. If x is 0.99, then 2x plus 3 is 4.98. So the closer x gets to 1, the closer the function gets to 5.
Right, so the limit as x approaches 1 is indeed 5.
Exactly. And since that matches the actual value of the function at x equals 1, we can say that fx 2x plus 3 is continuous at x was 1.
Okay, so we passed the three-part test.
We did. And the book gives another easy one. Fx, x soap at x equals 0. Do you want to try walking through this one?
Sure, so if we plug in 0 for x, we get 0 squared, which is just 0.
Perfect.
And then if you think about values of x getting closer and closer to 0, like 0.1, 0.01, 0.001, and so on, their squares are also getting closer and closer to 0.
Right. So the limit as x approaches 0 of x7 is also 0, which matches the function value.
So continuous at x equals 0.
You got it. Now how about something a bit more interesting? Fx, x, the absolute value function at x equals 0. This one might seem a bit trickier because of that sharp point at the origin.
Yeah, like visually it looks continuous, but it has that sudden change in direction.
It does, but remember, a sharp corner doesn't automatically mean a discontinuity. We still need to check those three conditions. So what's the function value at x equals 0?
Well, the absolute value of 0 is just 0.
Right. Now imagine approaching 0 from the left side of the number line. You're dealing with negative numbers, right?
Right, like negative zero point 0.1, negative 0.01, and so on.
Yeah. And what happens when you take the absolute value of those negative numbers?
They become positive, so you have 0.1, 0.01, and so on, which are all getting closer to 0.
Exactly. And if you approach 0 from the right side, you're already dealing with positive numbers. So their absolute values are just themselves also getting closer to 0.
So both sides are approaching the same value, which is 0, and that matches the function value at 0.
Exactly. So even though it has that sharp corner, x is indeed continuous at x equals 0.
Okay, that's pretty cool, and it makes sense when you think about it visually, too.
It does, and the book goes even further and says that the absolute value function is actually continuous for all real numbers.
How can we be sure of that?
Well, think about it. If you pick any point C that's not 0, then to the right of C, the absolute value function is just the line y IL x, and to the left of C, it's the line y equal x. Both of those are just straight lines, and straight lines are always continuous.
Oh, that's a neat way to see it. So those straight lines basically stitch together at x equals 0 to create a function that's continuous everywhere.
Precisely. Now, let's look at an example where we do have a discontinuity. Fx is 0, 1 if x equals 0, and we'll focus on what happens at x equals 0.
Okay, this one looks a bit different. It's like it has two separate rules depending on whether x is 0 or not.
Exactly. That's called a piecewise function. So if we plug in x we do directly, we use the second part of the definition, and we get f0 equals 1.
Okay, but then what happens as x gets really close to 0, but not quite equal to 0?
In that case, we use the first part of the definition, x is 0 plus 3, and if x is really close to 0, then x is even closer to 0, so the whole expression is basically getting closer and closer to 3.
Ah, I see. So the limit as x approaches 0 is 3, but the actual value of the function at 0 is 1.
Exactly, and since those two don't match, we have a discontinuity at x equals 0.
Okay, so even though the function is defined at 0, that single point where the value jumps up disrupts the continuity.
Precisely. It's like having a tiny hole in an otherwise smooth surface.
The book also mentions constant functions and the identity function, things like fx equals k, where k is just some number, and fx lex. Those seem pretty straightforward, right?
They are. If you think about their graphs, they're just straight lines, and straight lines are, as we've seen, continuous everywhere.
Right, makes sense. So far, we've been talking about continuity at a single point. What does it mean for a function to be continuous over its entire domain?
Well, it just means that it's continuous at every single point within its domain.
Okay, so it's like that pen lifting analogy, but applied to the whole function from start to finish.
Exactly. Now, there's a slight nuance when we're talking about closed intervals, like from point A to point B, including A and B themselves.
What's the difference there?
Well, at those endpoints, we can only approach them from one side. Like, at the left endpoint A, we can only approach from the right because anything to the left of it is outside the interval.
Right, and similarly, at the right endpoint B, we can only approach from the left.
Exactly. So for a function to be continuous on a closed interval, it has to be continuous at every point inside the interval. And at the endpoints, we only need to check the limit coming from the direction that's within the interval.
Okay, so it's like a slightly relaxed rule for those endpoints.
You could say that. Interestingly, the book also points out that if a function is only defined at a single point, it's automatically considered continuous at that point.
How come?
Because there's nowhere else for it to break, you know? It's just a single dot, and a single dot can't have any jumps or gaps in it.
Ah, that makes sense. Now, what about functions that have asymptotes like fx, x? The graph of that seems to have a break at x equals 0.
It absolutely does, and that break comes from the way 1x behaves as x gets closer and closer to 0. If x is approaching 0 from the positive side, like 0.1, 0.01, 0.001, the value of 1x is getting bigger and bigger, 10, 100, 1,000, and so on.
Right, it shoots up towards positive infinity.
Exactly, and if x approaches 0 from the negative side, like negative 0.1, negative 0.01, and negative 0.001, then 1x becomes more and more negative, negative 10, negative 100, negative 1,000.
So it plunges down towards negative infinity.
Precisely. And here's the key thing. Infinity, whether it's positive or negative, is not actually a real number. It's more of a concept, an idea of something unbounded.
So we can't say that the limit as x approaches 0 of 1x exists in the real number sense because it's not approaching a specific number.
Exactly. And because that limit doesn't exist, we say that fx on x is discontinuous at x equals 0.
Okay, but it is continuous everywhere else, right?
Yes. For all other real numbers, 1x forms a smooth curve with no jumps or gaps.
Piecewise functions, where the rule for the function changes depending on the value of x, can be a bit tricky when it comes to checking for continuity. The book gives some helpful examples.
They can be.
Oh,
Let's
yeah.
look at this one. F's x plus 2 if x error 1 by 2 if by 1 at x equals 1.
All right, so this function has two different rules depending on whether x is less than or equal to 1 or greater than 1.
Right, so to figure out if it's continuous at x1, we need to check if the value it approaches from the left is the same as the value it approaches from the right, and if those match the actual value of the function at x equals 1.
So if we're approaching 1 from the left, we're using the first part of the definition, x plus 2.
Exactly, and if x is a little less than 1, like 0.9, then x plus 2 is 2.9, which is close to 3. If x is even closer to 1, like 0.99, then x plus 2 is even closer to 3.
So the left-hand limit is 3.
Right, and now let's approach 1 from the right using the second part of the definition, by 2.
If x is a little bigger than 1, like 1.1, then by 2 is niddaline 0.9, which is close to main 1. And if x is even closer to 1, like 1.01, then by 2 is even closer to main 1.
So the right-hand limit is made of 1. What does that tell us about the continuity at x equals 1?
Well, 3 and main 1 are definitely not the same, so the two-sided limit doesn't exist, and therefore the function is discontinuous at x equals 1.
Precisely. That jump between the two pieces of the function creates a discontinuity. Let's look at another one. Fx, x soft plus 2 if by 1, 0 if x if 1 by 2 if by 1, again at x equals 1. This one explicitly defines the function value at x equals 1.
Right, it says f1, e0. Does that make a difference?
Well, it gives us one piece of the puzzle, but we still need to look at the limits. If we approach 1 from the left using x plus 2, what do we get?
As x gets close to 1 from below, x sub it gets close to 1, so x all plus 2 gets close to 3.
Right, so the left-hand limit is 3, and from the right using by 2.
If x is a little bigger than 1, by 2 is close to minus 1, and as x gets closer to 1, by 2 gets closer to minus 1.
So again, we have a mismatch. The left-hand limit is 3, and the right-hand limit is minus 1. That means the two-sided limit doesn't exist at x equals 1, even though the function has a defined value there.
So it's still discontinuous. That defined value at x equals 1 doesn't bridge the gap, so to speak.
Exactly. It's like trying to patch a hole with a single point. It doesn't quite work.
Okay, let's try this one. fx, x plus 2 if b0 minus x plus 2 if b0. What's happening around x equals 0, 0?
Notice anything particular about this piecewise function?
Well, it only has definitions for x less than 0 and x greater than 0, but not for x equal to 0.
Exactly. So we can't even talk about continuity at x equals 0 because the function isn't defined there.
Right, but we can still look at continuity at all the other points.
Absolutely. And since both x plus 2 and negative x plus 2 are just straight lines and straight lines are continuous, this function is continuous everywhere in its domain, which is all real numbers except for 0.
So it's like two continuous lines, but with a gap between them.
A very poetic way to put it. Let's do one final piecewise example. F x ct if x equals 0, x if phi 0 at x equals 0.
All right, so this one has a rule for x greater than or equal to 0 and another rule for x less than 0.
Right. First, let's check the function value at x equals 0. Which part of the definition do we use?
Since it says greater than or equal to 0, we use x0, so f0 being equal to 0 is 0, 0.
Perfect. Now let's approach 0 from the left, using the x rule.
Well, if x is getting closer and closer to 0 from the negative side, it's just approaching 0.
Right, so the left-hand limit is 0, and from the right, using x squared.
As x gets close to 0 from the positive side, its square also gets close to 0.
So the right-hand limit is also 0, and all three of those match. The left limit, the right limit, and the function value at 0.
So this piecewise function is actually continuous everywhere, even though it has two different rules.
It is. The two pieces meet up perfectly at x0 without any jump or gap.
Now, the book introduces something called the algebra of continuous functions. That sounds intriguing.
It is. Basically, it gives us some handy rules for combining continuous functions. Like, if we know that two functions, let's call them f and g, are both continuous at a certain point, what can we say about their sum, difference, product, and quotient?
I'm guessing those combinations are also continuous at that point.
You're exactly right. Theorem 1 tells us that if f and g are both continuous at a point C, then f plus g, fg, and feog are also continuous at C.
Okay, that makes sense. What about division?
For fg, there's a little caveat. It's continuous at C as long as the denominator, g of C, is not 0. We can't divide by 0, remember?
Right, of course. So this means we can build up more complex continuous functions from simpler ones, kind of like building blocks.
Exactly. Think about polynomials, like x ups plus 3 by 2. They're just sums and products of constants, which are continuous everywhere, and the function x, which is also continuous everywhere.
So by this theorem, all polynomials are continuous across the entire real number line.
You got it. And that leads us nicely into rational functions, which are just fractions where the numerator and denominator are both polynomials.
So like x of x plus 1 by 2 would be a rational function.
Exactly. And based on what we just discussed, a rational function will be continuous everywhere except for those pesky points where the denominator is 0.
Right, because at those points, the function is undefined.
Precisely. Okay, what about our good old trig friends, sine, cosine, and tangent? Are they continuous?
I'd hope so, considering how often we use them.
Oh, good news. Sine and cosine, sin x and cos x, are indeed continuous everywhere. Everywhere. The source mentions a neat way to show this for sine. It starts with the fact that as x approaches 0, sin x also approaches 0. Then, using some trig identities, you can prove that for any value c, the limit of sin x as x approaches c is equal to sin c, which means it's continuous.
And cosine probably follows a similar logic, right?
It does. Now, tangent, tan x, is a bit more complicated because it's defined as sin x, cos x.
Right, so it's a quotient.
Exactly, and remember our rule for quotients. They're continuous except where the denominator is 0.
And cosine is 0 at those angles where the x-coordinate of a point on the unit circle is 0. Right?
They're on fire. That's at odd multiples of 2, like 2, 3, 2, next, so on.
So tangent has discontinuities at those points,
Mm-hmm.
which makes sense when you think about its graph with those vertical asymptotes.
It all connects beautifully. Now, let's talk about composite functions, where you basically plug one function into another, like f g x.
Yeah.
Theorem 2 tells us about their continuity.
So like sin x would be a composite function, right?
Yep, perfect example. Theorem 2 says that if the inner function, in this case gx equals xxa, is continuous at a point c, and the outer function, in this case fu basic m, is continuous at gc, then the whole composite function, sin x, is also continuous at c.
Okay, so it's like a chain of continuity.
Exactly. And in this example, we know that x Busher is a polynomial, so it's continuous everywhere. And we know that sine is continuous everywhere. Therefore, sin x is also continuous everywhere.
Cool. The book is another example that looks a bit more intimidating. 1x plus x.
Yeah, that one looks like a mouthful, but we can just break it down layer by layer. The innermost part is x, the absolute value, which we know is continuous everywhere.
Okay, so that's our starting point.
Right. Then we have 1x plus x. That's just a sum of continuous functions.
Right.
The constant 1, which is continuous everywhere, the function x, which is also continuous everywhere, and x, which we just established, is continuous everywhere.
So by the algebra of continuous functions, 1x plus x is continuous everywhere.
Exactly. And finally, our original function is just the absolute value of that whole thing, 1x plus x. And since the absolute value function is continuous everywhere, and the thing we're taking the absolute value of is also continuous everywhere, the entire composition is continuous everywhere.
Okay, so even though it looks complicated, we can just break it down step by step.
Exactly. It's like peeling back the layers of an onion, but without the tears, hopefully.
One last function to consider for continuity. The greatest integer function, written as fx equals x, this one has a graph that looks like a staircase, right?
It does. The book points out that for any number c that's not an integer, the greatest integer function stays constant in a small enough interval around c. Like between 2 and 3, the greatest integer is always 2.
Right, because the greatest integer less than or equal to any number between 2 and 3 is 2.
Precisely. And since constant functions are continuous, the greatest integer function is continuous at all those non-integer points. However, at the integers themselves, that's where the jumps happen.
So like at x, x2, what happens?
Well, if you approach 2 from the left, you're dealing with numbers slightly less than 2, and their greatest integer is 1.
But if you approach 2 from the right, you're dealing with numbers slightly greater than 2, and their greatest integer is 2.
Exactly. So the left-hand limit is 1, and the right-hand limit is 2, which means there's a jump discontinuity at every integer.
Okay, so the greatest integer function is continuous everywhere except at the integers, where it has those step-like jumps.
You got it.
All right, we've covered a lot of ground with continuity. Let's move on to differentiability, which is all about derivatives, and the book reminds us of the definition right away.
Yeah, and it can seem a bit intimidating at first, but it's basically about finding the instantaneous rate of change of a function at a particular point.
And the way we do that is by looking at this limit, f ν c plus h,
Yeah.
ch, as h approaches 0, where c is the point we're interested in.
Right, and that expression might look familiar. It's essentially the slope of the line connecting 2 points on the graph of the function, c, fc, and c plus h, fc plus h.
So h is like the tiny change in x, and we're seeing how much the function changes in response to that tiny change.
Exactly. And as h gets smaller and smaller, Those 2 points on the graph get closer and closer together, and that line connecting them starts to look more and more like the tangent line at C.
So the derivative is the slope of the tangent line at that point.
Precisely. It's the instantaneous rate of change, the slope at that exact moment.
But the source emphasizes that the derivative only exists if this limit exists.
Right. Just like with continuity, there are certain conditions that need to be met for this limit to make sense.
What are those conditions?
Well, we have to consider approaching zero with our little change h from both the positive side and the negative side. Getting slightly larger than C and slightly smaller than C.
Right, like with those one-sided limits for continuity.
Exactly. So both of those one-sided limits for the derivative have to exist, they have to be finite numbers, and most importantly, they have to be equal to each other.
So if they don't match, or if one of them shoots off to infinity, then the derivative doesn't exist at that point.
Precisely. And if the derivative doesn't exist, we say the function is not differentiable at that point.
Now, Theorem 3 makes a crucial connection between differentiability and continuity. It says that if a function is differentiable at a point, then it must also be continuous at that point.
That's a really important result. Think of it this way. If a function has a well-defined finite rate of change at a point, meaning it's smooth and doesn't have any sharp corners or jumps there, then it can't suddenly have a break in its graph at that same point.
Right, like it can't suddenly jump up or down if it has a nice smooth tangent line there.
Exactly. The book's proof basically shows that if that limit for the derivative exists, then the difference between f of x and fc has to get smaller and smaller as x gets closer to c, which is exactly the definition of continuity.
Okay, so differentiability implies continuity. But is the reverse true? Does continuity imply differentiability?
Ugh, that's the catch. Doesn't always work that way. A function can be continuous at a point without being differentiable there. The absolute value function at x equals 0 is the classic example.
Right, we saw earlier that it's continuous there, but what happens when we try to calculate its derivative at x equals 0?
Well, we look at the limit of 0 plus h0h, which simplifies to hh as h approaches 0.
Okay, so what happens if h is positive?
If h is positive, then hh, so hh is just h, which is 1.
But if h is negative?
If h is negative, then h is h, so h becomes h, which is negative 1.
Ah, so the limit from the right is 1, and the limit from the left is made of 1, and those don't match.
Exactly. So the two-sided limit doesn't exist, meaning the derivative of x at x equals 0 does not exist.
Which makes sense when you look at the graph, because that sharp corner at x is 0 means there isn't a single well-defined tangent line there.
Precisely. Continuity just means there's no gap or jump, but you can still have those sharp corners that mess up the differentiability.
Right. Next up is the chain rule, which is a powerful tool for finding derivatives of composite functions, those functions within function situations.
Theorem 4 lays it all out for us. If we have a composite function like fx equals v ux, where ux is the inner function and v is the outer function, and we let t equals ux, then the chain rule tells us that df bx equals d dt. Okay, I think I'm following me. It's like saying to find the derivative of the whole thing, you multiply the derivative of the outer function by the derivative of the inner function.
You got it. And you can think of it like gears turning. The rate at which the outermost gear turns depends on the rate at which the inner gear turns, and the chain rule connects those rates.
The book has some examples that might help make this clear. Let's try fx, x, say.
Perfect example. So our inner function ux is xxx, and our outer function vt is sint, where we're using t to represent what gets plugged into the sine function.
So t xx.
Exactly. Now, what's the derivative of sint with respect to t?
That's cos t.
Right. And the derivative of xx with respect to x?
That's 2. You're on a roll. So using the chain rule, the derivative of sin with respect to x is cos 2u, 2x. And since t equals x, we can substitute that back in to get 2x cosine.
Okay, so the chain rule basically helps us deal with those nested functions.
It does. Let's try another one. Tan 2x plus 3.
So here our inner function ux is 2x plus 3, and our outer function vt is tant.
Perfect. Now, the derivative of tant with respect to tit is second t, and the derivative of 2x plus 3 with respect to x is just 2.
So by the chain rule, the derivative of tan 2x plus 3 is second t 2, which becomes 2 second 2x plus 3.
You're getting the hang of it. Ready for one more, a bit more nested?
Hit me with it.
Okay, how about sin cos